Welcome back, everyone. We're gonna, since you all have been so wonderful at participating, we're gonna do a quick coffee break for 10 minutes. There's another Slido poll that should be open in a second. So if you're able to hop on real quick and do that, it's great. And we'll see you all back here at 1:55. Thank you.
Like a lunar surface. Oh, okay. So lunar surface and also lunar orbit position navigation timing. And in this category, I have like 3 projects. And first is to try to set up a GPS-like system for the moon, leveraging LunarNet. The second project is to see, how to take advantage of the terrestrial GPS signals for lunar either surface or the orbit users. And then third project is in collaboration with NASA JPL as part of the Cadre mission, which will be like sending a swarm of 3 small robots to the moon surface in 2024.
Very exciting. 2024 is coming up. And Julie, go ahead.
I'm Dr. Julie Obenauer-Motley. I'm a senior national security analyst here at the Applied Physics Lab. And I started as doing machine learning, actually with predictive geospatial analytics, and then moved into the responsible AI side of things. And so a lot of my work is helping our sponsor base here at APL understand when and how they can reasonably use AI and machine learning and then teaming, how to do it in ways that get us good teaming and effective teaming, not just sort of teaming, and then how we can optimize those partnerings to get the effects we want. I call it a little bit of the bill of goods detection piece when helping our sponsors understand when we're maybe being sold something that isn't as effective as we think it's going to be. And I think the contributions I have here come from my work on looking at how we do teaming and pairing and how we take the psychology of human behavior and what we would like our machines to do and how we evaluate those together.
Very, very cool balance of expertise we have on this panel. So we can jump in with the first question. We talk a lot in the lunar surface technology community about partial autonomy and full autonomy are terms that you hear thrown around a lot. Any thoughts on if there will ever be such a thing as full autonomy or what that might mean to you?
I think it's a matter of time that we're going to have full autonomy with the development of AGI or even super intelligence at some point. And so I think it really depends on the time frame, but I believe full autonomy is possible.
Grace or Julie, any thoughts on the term full autonomy? If that's applicable to some use cases but not others,
Yeah, I also believe full autonomy is possible. And then I think it also depends on what's the need for the system. Maybe for some system, they do need the full autonomy, and maybe some other system, maybe because of the trade-off, right, among the full autonomy, the cost, the complexity, maybe, just a partial autonomy could be sufficient.
Yeah, I agree strongly with Grace. I think that while it is feasible, going to depend heavily on what it's for and what the risks of using full autonomy are, as opposed to other autonomy schemes we may have.
Okay. And so even if we do achieve full autonomy, will there always be a human in the loop?
I think, again, that is super domain and use case specific and is really going to depend on what's the risk we're comfortable with, and when it fails, what does degradation look like? Human in the loop as we get more advanced may not actually be the sort of technological failsafe we think it is, especially when we talk about things like communication delays and response times. So I think that there will always be cases where that makes sense, but I think we are going to have to find new and different paradigms for how we ensure safety and security of our systems that don't require a human to step in and press a button when they need to.
Right. And any thoughts on how we sort of go about distinguishing what activities should be done autonomously and which, should be human dependent, either methods for delegating those tasks or even identifying that's use case specific. Grace, in regards to your existing projects, any thoughts there on delineating, what is an autonomous activity and what is a human-tended activity?
Yeah, that's also a very good question. Again, I think it depends on the need. There are pros and cons for both approaches. If we achieve full autonomy, right, it's a fully autonomous, then I think in some rare cases, if there are extreme cases related to safety or like robustness, maybe, in case things go wrong, you may still want humans to take control. But on the other side, right, sometimes humans can make mistakes too, right? So we can have errors, or sometimes deliberately, human can make mistakes. I think early on today, Professor Jim Bellingham mentioned, right, in aviation, a lot of the accidents actually made by human, could be purposely suicidal, or and then cause the airplanes to crash. And then yeah, so it's just the two aspects of this problem.
I think there are certain aspects. It's always better to have human involvement because we as human, we have many considerations which a machine may not have the same consideration. That's why what we did was we put something called motivation function into a robot, and so the robot can kind of share the same thinking as human. But there are certain aspects, when you look at a high level, just the search space is so huge. It's still much better to have human be involved in that process.
I think that, again, this is really domain specific in terms of what's the technology doing and what's the risk of failure. So what authorities have you given the technology to act? What are the technical constraints on the systems? And then what are the risks? There are definitely cases in which we're likely to see that human off of the loop, human not involved, is probably safer due to human response times, the way we maintain attentional focus, the way we respond to alarms are having to take over in the extent or in the instance of issues. Human on the loop may be a paradigm that we need to figure out what is the risk, what does degradation look like, and then how do we want to respond from there, what actually creates safety in the system versus just puts a human in the system.
Right, very interesting. I love the dynamics and the answers, right? It's very representative of the community. Let's see, in your past work, I mean, any hard-won lessons learned in designing and integrating systems where humans interact with autonomous systems? We're thinking specifically on the moon, so that'd be astronauts interacting with robotics in space environments, but anything that really comes to mind in that regard?
Yeah, I would say, with human in the loop, I would say it's not just about, understanding about the human, but also maybe predicting the human behaviors. If the astronauts are going to work with the robots, right? And when the robots have to make the decisions about what to do next. So that means not only the robots need to know what the humans are currently doing, but also have certain prediction about what the humans will do for the next time step, or in kind of even a little bit longer future, so that the robots can, decide about what they should do accordingly.
Yeah, the hardest problem that we ran into, just like Grace said, is always human intent. Because there's certain things that robots need to understand what is human intent, but very often human intent is very vague and also situational dependent. So robots need to continue to observe and adapt, which is very difficult.
Don't have experience in the space domain, but I can say that what we're finding in the DoD domain is how we get them to understand interacting with this as a teammate versus as a tool. And we're trying to figure out how to understand the way humans actually bond and interact with robots from a psychological perspective. So if this is something you are having to live and work with, how do you as a human make the separation between what is a machine, what is a tool, and what is sort of a companion or a trusted agent working with you?
And when you're testing out these sorts of collaborative systems, what sort of facilities do you use?
Well, for us, like what we show, we use a basic virtual test environment. It's a collaborative virtual test environment that we build on top of the NVIDIA Omniverse. So it's kind of like a metaverse environment where everybody can contribute. And one thing we learned is students really good at innovating, creating new idea. And when you have a common platform, everybody start to innovate together. And then the kind of thing that we do is we have human and robot, and our goal is to have arbitrary model all working together. So with that really help us in terms of getting human and robot and all the other object working together.
Yeah, I want to echo what Edward has said. For us, we also have some projects about autonomous driving. And then for that, we test in also the simulation platform, because this is like a safety critical system, right? And then anything you want to test, that means there's a risk of failures or collisions. Then it's safer to test in a simulation, like high fidelity simulation environment. And also when you're testing the high fidelity simulation environment, you can also test for the edge cases or the rare cases. As a matter of fact, actually, we also have some work, for like see how to quickly and better way of finding these failure cases. So that's a little bit counterintuitive, because normally if you think about safety, right, and robustness, you want your optimization, or your goal would be try to avoid those failure cases. But in our study, when we try to really find these edge cases, we have some kind of reinforcement learning algorithm. And then the reward function, or the goal is actually to reward the learning system to quickly find those failure cases.
In this environment, we can simulate thousands and thousands of different possibilities. And if we look at what's happening with the digital twin development right now, people are taking directly from simulation to hardware implementation. So there's no need for intermediate testing anymore. And this is very critical for human safety, kind of human robotic collaboration kind of operation.
We've worked some with Unreal Engine as our digital test bed, but we have also been trying to work on how do we use that as synthetic data to start working with, that we can then match to real world data for augmentation pieces. Partly because we have been pushing for a not synthetic only approach when putting together kind of our testing and evaluation master plans. But again, my domain's a little different on that one.
Yeah, your answers are really resonating with a lot of what we discussed last month at our Lunar Proving Grounds workshop, and that how you test out these technologies or prove out these technologies is not always necessarily a physical facility that you go and conduct hardware testing at. It can be, and it can be useful in a lot of cases, but a lot of opportunity is created in simulated environments, and your responses are definitely proof of that. Speaking of data, Julie, what sorts of data are needed when you're trying to test out or develop a collaborative system with mobility, whether on part of the human, if there is a human in the loop, or on part of the autonomous hardware that you're trying to test?
Well, the biggest problem that we run into, and we're still having the problem, is actually the multi-model data set problem. Because even when we use like CLIP type of based system, you have like hundreds of millions of data, but for the kind of data that we need, a lunar kind of simulation is very, very difficult, very, very small amount of information. Even we can do all the multimodality cross training, it's still lagging And so in order for all these collaborative systems to work together, we need a large multimodal model that can fit our lunar exploration kind of environment. And with that, everybody can share that foundation model. Everybody will benefit from it. That's the biggest problem that we currently have.
Yeah, I think I agree. So I would say, what the data, or the data will be in two categories, right? And one is the sensing category. The other is the communication category. For the sensing part, right, depends on the need, and then you may have different sensors, like for, given my area is about PNT, right? For PNT sensor, you can have vision sensor. We also had a talk early today about using vision sensor for moon surface exploration. You could have inertial measurement sensors. You could leverage some satellite navigation, like a GNSS or GPS sensors, right? And then once you gather all these sensing data, and then the next category is the communication, and then what to communicate, right? And then you don't want to overload the communication so that it's too overwhelming. You want to only send the enough amount of data, but that you also want to send sufficient amount of data, and that can enable this collaborative robotics tasks.
So for us, the pieces of data that we're trying to collect on right now are actually how our human teammate is going to behave. And I think we mentioned driving specifically, or movement. One of the things that's great about machines is you can instrument them to kind of collect data on themselves as things go. Humans are much harder to instrument and collect data on that way, and in some ways are less predictable. And so we're looking to, and if you were in my breakout group in the last one, I talked about this, we're looking to the psych and anthropology research as much as we are looking to kind of what's the hard data we can get on understanding what the human piece of the human team is. Why do we react the way we do? How can we be modeled in sim in ways that allow us to actually train a robot based on what a human is likely to do, or where we are kind of are likely to be unpredictable. So that's the piece that we are really focused on in terms of what data actually needs to be generated there for us to start answering the human piece of this teaming.
For sure. And from a responsible AI perspective as well, every human's different. We are humans. That's kind of the point, right? So how do you create this generalizable or predictable capability for humans when we are so dynamic in and of ourselves?
How do we set up the machine so that when we are unpredictable, it can react?
How do we set up the machine so when we are predictable, they can
when
react?
we are unpredictable.
Mm-hmm. Got it. So that, let's see, small n data, sensor data fusion, and machines reacting to our unpredictability, because the constant is chaos, I guess, when it comes to humans. All right, and in terms of terrestrially, do you see any sort of analogous work being done in terms of collaborative robotics, swarms, things like that, that could be applicable to lunar domains?
Yeah, for example, for drone swarms, right? That's can be used terrestrially for, say, surveying an area for, say, wildfire detection. And then, there's also the collaborative like robot arms, like to help, like that's in the medical robotics domain, to help doctors to do like surgeries, operations. And then, there are also, you could also like in manufacturing, right? In factories, and you could have collaborative robots to work with humans, like either for like assembly or for like a warehouse management. So there are a lot of applications on Earth, and then, for space system, we could get inspired or learn some lessons from those applications.
The autonomous vehicle world is also doing a lot of this trading control piece. How do I cleanly go from my vehicle being largely in control of this situation to me being able to quickly take over and be largely in control of the situation at speed, right? Where speed is sometimes 70, 80 miles an hour, and I have to miss an emergency vehicle. So we are starting to get at those pieces, some ways in lab, and then some ways, whether we're ready for not in real world testing as well.
Any thoughts, Ed, on translational innovation from Earth?
Well, there are many of that. I think for the terrestrial and in space. In space, I think a good example is the Cadre mission, NASA Cadre mission. That's a good example. And then I think Grace mentioned that the collaborative drone. I think the emphasis the interest that we have is more than swarm. It's more than collaborative autonomy, because the different robots actually doing a little bit different things. So that I think it's beneficial for lunar kind of exploration, where they will see different things and do different things.
Got it. And so when there is a human in the loop, are there notable, not are there, but what are the notable safety concerns when you've got human in the loop? Let's say for the lunar surface, that could be partnering with an astronaut collaboratively on the surface. That could be connecting with a mission ops team or some other Earth-based team, but still very much so humans are in the loop. What sort of keeps you up at night about, human integration with autonomous systems?
I like the comment Julie earlier on, touch on, human could be unpredictable, right? And how to understand and that that unpredictable behavior of humans, and how to make the system still safe, given human can be unpredictable. And then, how to also, Edward early on touched on this, how to incorporate the human intent in the robotics, decision making. And these are I feel that the important issues to think about.
The biggest piece in this sort of collaboration and teaming that I would say keeps me up at night is the way we think about the human partner as adaptable and picking up where the robot partner can't. And in a lot of ways that can be really meaningful, but also the job of both is to partner and do things that are within a skill set that they have. And we tend to forget that and put humans in roles that are overseers, or, oh, well, the robot can do it up to this point, but then the human has to do a thing, and then the robot takes over, without looking at, okay, what would actually be kind of the better vision of labor and the responsibilities to ensure that the human teammate is also being set up for success, not just being set up to prevent the machine teammate from failing.
You have something you wanted to say, Ed?
Well, I don't really have much to add, but my experience in the past is humans really don't want to be bothered with the thing that they think you understand. So when human work with robot, and when robot does not do what the human think the robot will do, then there could be a kind of safety related issue. So with that, it could get back to intent issue, and then with that get into the in terms of the kind of simulating and testing a variety of different environment, different kind of safety concern in kind of thousands of different possibility, and learn from that. These are very minor kind of differences that today we basically kind of encode a lot of this information in the latent space that we just inherently understand. But as I said before, that we're missing a lot of data, so we can't really encode it very well. We can only generate synthetic data to do a lot of these encoding, and I think collecting data and put it into virtual environment will be the thing that will drive to mitigate some of these concerns.
Got it. And when you are doing that modeling towards the end of trying to mitigate risks and try to prevent these concerns from actualizing, what sort of safety measures do you keep in mind? What sort of edge cases are you testing for?
Well, we use synthetic environment, as you have seen, to generate many cases, and we use it to test edge cases. I think I remember earlier Dr. Raman was talking about auto distribution cases, so auto distribution kind of data, and those are the things that we try to look for and try to anticipate, and trying to synthesize those conditions, and that we find to be very useful, recognizing all the distribution cases and generating all the distribution cases.
Yeah, I totally agree. I think it should be, the safety metrics should be in 3 categories at least. The first is how to make the system safe against different uncertainties. There could be the sensing uncertainties, communication uncertainties from both the humans as well as the robots. And then the second category will be how to ensure safety against failures, right? I think I had also mentioned about this, to avoid these failures and then the rare cases. And then the third category is like how to ensure the safety against the extremes. And then in terms of the safety measures, actually, there are a lot of things we can also learn from terrestrial systems. For example, for aviation, right? Currently, I take air travel, and then I feel pretty safe for that, right? There are a lot of the safety measures from aviation. For example, not only we need to know, say, the system performance or the accuracy, but also we need to know the confidence of that accuracy, right? And then, to say, airplane navigation sensor has a 5-meter accuracy, it doesn't make much sense unless you pair it up with the confidence level. Say, so we are like 99.99999, like a 69% confident that the airplane navigation localization suite could achieve this 5-meter accuracy. So a lot of these safety measures, we could, for space system, we could learn from the terrestrial systems.
Other piece there, and I think Grace touched on this some, is ensuring that graceful degradation is built in. So, when we're talking about it has a 95% success rate, and this is our confidence in that, what happens that other 5% of the time, and what does that degradation look like? And that's obviously very context dependent, right? How comfortable are we with degradation, and how do we need that to go in a way that enables us to maintain safety in systems where that's important? So ensuring not that we're just trying to prevent problems from happening, but have a degradation ramp for when that does happen.
Appreciate that.
Yes,
Okay.
and then actually inspired by like Julie's comments, and I feel there's another aspect, right? And then, for the collaborative system, there's this built-in redundancy. So maybe we don't need to aim for 100% of safety, right? If we say have a swarm of small satellites, maybe it is okay to lose one satellite, if we still have the majority of the swarm functioning, right? I think that's the beauty of the collaborative system, because you don't have a single point failure, and then that's already inherent built-in robustness for safety.
Appreciate that. Yeah, we hear a lot about risk tolerance, but I like getting into these specifics of graceful degradation, multiplicity, sort of acceptable failure. Not pretending failure does not exist, or not that it's all or nothing, but it's very often somewhere in the middle. So what middles are we okay with, or do we foresee, or have we trained or tested for? What difficulties do you foresee collaborative systems in space experiencing that we don't experience here on Earth? Anything unique to the space environment, the types of operations that we will be having, the TRL level, or just the sheer amount of experience we have operating, let's say, in the lunar surface, that you think collaborative systems will particularly be dealing with?
Oh, sorry, is your question about like what's the challenges of the lunar system compared to the terrestrial system? What's the challenges?
Yeah, unique challenges and leveraging collaborative systems on the lunar surface as opposed to on Earth.
Yeah. Of course, for the lunar surface, the resources are limited, right? You have limited power, limited computation. On Earth, there are a lot of applications you can leverage, say, edge computing or cloud computing. And then what's more, I think, in terms of the testing, right? For example, for autonomous driving cars on Earth, right? And there are all these autonomous driving companies that have been testing for millions and millions of miles, right? In Arizona, in different parts, right? And then recently, they also started to test in safety of San Francisco with more like a complex terrain, like a situation. However, say if we want to do something on the moon, we just cannot afford to test like a few million miles of driving on the moon. So, in terms of designing the system, right, we have to make sure to consider all the safety and all these like a safety and other like considerations in advance. We cannot expect that we can try to have this many iterations and then test a lot and then iterate and improve the system.
I would just be speculating here since this space is not my domain.
Anything top of mind for you, Ed?
No, I don't have anything to add to what Grace said. Yeah.
Grace, you mentioned cloud computing in particular, which comes up quite a bit within the LSIC excavation and construction group. We have a subgroup focused on autonomy that Al-Hassan, who was facilitating the previous session, and myself, we both co-lead. And a lot of our conversations end up driving towards compute resources. It's sometimes less so, we have self-driving car algorithms, not exactly the same terrain, but we've got some lineage there in terms of it being done before. But on Earth, I hand Amazon my credit card and I can use cloud compute resources and spin something up, in an hour, in an afternoon. And what does that look like on the lunar surface? Who are those providers of compute resources, and how does that affect my collaborative systems that depend on autonomy or the iteration, as we gain more context of the environment that we're operating in. Something that comes to mind a lot. We have a lot more questions and answers on that front. But if or when that changes, feel free to reach out and keep that conversation going.
Yeah, that's definitely good to know, right? And a lot of that it also depends on the need or the strategies. And for example, I know NASA has been trying to contract with, I believe, Nokia to set up the LTE like Wi-Fi system on the moon surface, right? That's like about building infrastructures, and that will really help with a lot of the communication. And then who knows, maybe if there's a need given, looks like there will be 400 missions like a plan for the next decade among different government agencies and like private sectors, right? But maybe, at a certain point, like a big computing like a cluster or center, it could be built on the moon surface to help with this moon cloud computing as well.
I think the computing is also depending on how we implement things. For example, like the example that we show using differential physics. If we want to do simulation, it takes a fairly big computer to run for a couple of hours to get the particle level simulation. But when we use the neural network enhanced physics model, we did that in 400 milliseconds. So and very little computing resource involved. So I think we need to look at how we want to implement which part need to. I think that will reduce some of the requirements.
All right, and I'll end on one last question. What challenges do you see us facing as we begin implementing more collaborative systems in our lives?
Regularly follow my Roomba around my living room, trying to get it to not fall off the steps. I think that really interesting and actually fun question, because as we introduce these collaborative systems into the world, it's sort of anything can happen, right? We talk about humans are unpredictable, but environments are unpredictable, and building in, again, that resiliency and that degradation, because it doesn't matter if I get a text from my Roomba that says it somehow fell off a cliff in my living room, which happens with alarming regularity. It does start to matter when we're looking at more complex systems that have more impact on our lives. And that's, we see it with digital assistants and the questions we start to ask them. How do we make sure that they are actually serving the human, or working with collaboratively and effectively the human teammates that they are here to help, as opposed to being a hindrance or just unusable?
Yeah, I would say, safety is very important, right? And then that's a safety against all these sensing communication uncertainties, and safety against extreme cases, and also safety against failures.
For us, the research that we're dealing with, low TRL level research, is trying to figure out, how does motivation function work in this environment? Because for human, that we can do a lot of different things, but we may not do it because we don't want to go to jail or whatever. So same thing with robot. Can robot actually work with us? Can we just tell robot a few motivations and then have robot learn from it? So if we can do it, then robot may be able to work with us, in a much more friendly way.
Makes sense. All right. Thank you all for your time and your wisdom and the gems dropped in today's session. And I will hand it back to Danielle.
Thanks.
Thank you.
Yeah, wonderful panel. Thank you all so much. Christina, if we're able to share slides again, I think we're going into another coffee break. This one will just be 5 minutes long. So we'll see you all back here at 2:45. There's another Slido poll if you're interested. And we'll see you in a minute. All right, welcome back. Oh. Welcome back, everyone. Yep, so I think we're moving into presentations now. Sarah, if you're around.
Eddie's here. I'm ready when you are.
Hey, Eddie. Yep. So first up, we have Eddie Tunstall from Motive Space Systems on the Human Collaborative Robotic Autonomy Earth-Moon Maturation. So please take it away if you'd like us to share slides, or if you would like to share slides, let me know.
I'll attempt to share mine, and I'll keep my video off in case that causes any bandwidth issues.
Sounds good. Thank you.
All right. Let's see here. Okay, do you see my slides?
Yes, sir, we do.
Okay, I'll go ahead and get started then. So I'm Eddie Tunstall. I'm CTO at Motive Space Systems, as was mentioned. I'm going to get right into this. I know we have about 10 minutes to go through this. Firstly, I'll just point out that Motive Space Systems is primarily a hardware company. We support robotic autonomy with the essential space-rated hardware, if you will, and ground prototype hardware that autonomy tends to run on. And we tend to focus quite extensively on robotic systems in that regard. To learn more about Motive, if you're not already familiar, the website URL is at the bottom of this screen. So collaborative autonomy, I have a couple of premises here that I'm going to just mention to sort of set the context for what I'm going to talk about here. So my claim is that there's no shortage of autonomy algorithms and techniques for collaborative robotics, including as involved with humans and so forth as part of the system. The robotics research community has been looking at things like multi-rover capability for planetary exploration for quite a while, actually. This has been a vibrant focus area in terrestrial robotics to begin with. And so it easily translated over in terms of interest and capability development to future applications in space and on planetary surfaces. But I claim that in lieu of mission opportunities that have involved more than one surface asset to date, the related capabilities have not been matured or have really had a chance to mature to space mission readiness. And this is sort of the state that we're currently in still. There's a lot of technology out there available and algorithms and so forth, but they haven't gone through the gauntlet of transferring from the current state of capability to what could actually be used on space missions. So what I'm going to talk about in this brief talk is really just trying to highlight some of that representative R&D that has been going on over the past decades. But in order to do that, I'm sort of going to flip through and whiz through, if you will, a bunch of different slides, almost like a picture show of sorts. And at the end, I have some conclusions that I'll spend a little bit of time on. So I've prepared my slides in such a way that there are citations of references on most of them, and mainly to make this usable as a resource after this workshop, so that people can look back and look up some of those past R&D activities. So pardon my flipping through the subsequent slides in a relatively quick manner. So first off, I'll point out that the science community got pretty close some years back with a two-rover concept that was proposed at that time by the MEPAG group for a 2018 mission opportunity. It was later canceled though, but nonetheless, for technology developers in this area, such as myself and many others, it was encouraging to see a space agency getting to the point where they would actually have multiple assets on the surface that could collaborate if that were part of the mission. And so that more or less continued to fuel ideas and activity towards researching these types of systems in the first place. This also led to a number of different types of scenarios and system architectures whereby you could have one rover doing things like ground surface level surveys. In this case, this is a mobile spectroscopy using open path spectroscopy, where you're shining the laser off to a stationary retroreflector, but with the idea that you could also extend such a system to the point where that retroreflector doesn't have to be stationary. It could be on another mobile platform, and these surveys could be basically done in tandem in multiple locations on a planetary surface. There's also been a number of efforts to look at cooperative utility robots that do various things from excavating to doing a cooperative assembly of photovoltaic tents, for example, on a planetary surface. These are all images and depictions of past studies and actual field work where folks like organizations like JPL, Oak Ridge National Lab, CMU, and many others, this is all just representative, have been engaged in these activities. And you see from the references at the bottom of the slide, this dates all the way back to 1998, and certainly even before that. So there's been lots of work going on. NASA Ames also had their K-10 robots in past field tests doing cooperative or collaborative types of activities. This was a case where at Moses Lake Sand Dunes in Washington, a couple of rovers performed scouting and survey operations equipped with LiDAR images and GPR. And remote lunar surface operations were simulated in this case with ground control team located at the NASA JSC in Houston. So again, this activity falls into this category of using more than one surface asset to do collaborative or cooperative types of activities. JPL dug pretty deep in this area as well in past years. They had something they called the robot work crew, as well as the robot construction crew, looking at doing construction as well as doing access to extreme terrain using a set of robots that would collaborate together. There's a stream of publications that they had put out back then, but all built around this campout architecture that JPL developed. It's also worth noting that that particular architecture was later advanced and combined with a high-level planning capability in the form of something that they called Caracas, and used on multiple unmanned sea surface vehicles to do collaborative autonomy as well. So again, these things have been around and been fielded to at least mid-TRL in many cases. There have been swarming concepts as well, and those in particular using small, simple, and low-cost rover systems. In the past, while I was at APL, there was at least one study where we were focusing on something like that for accessing and doing surveys within PSRs. And currently today, TU Delft's Luna Zebra project is ongoing, where they're looking at doing similar on the lunar surface using a swarm of small, low-cost, and simple rovers. Even hierarchical team structures have been thought about and investigated to some degree. I saw something earlier in the chat questioning whether this has been sort of thought of. Here's a case where you might have astronauts or a lander or even an orbiter as a so-called central station for command and telemetry interfaces. And you might have a set of robots that have a certain level of autonomy in terms of navigation and planning, and could also do task allocation and coordination for a team of rovers that they actually oversee. And then smaller rovers with minimal computation and communications resources that work in groups supervised by a higher level, more capable robot. So these types of architectures have been explored as well. This sort of harkens back to about a decade ago, more than a decade ago, when NASA was focused on the moon again, and in particular in the Constellation program. And this is a sort of NASA reference scenario depicted here on this slide, where we have a number of different surface systems, some of which are robots, some of which are humans. And the associated NASA prototypes and field trial activities that were going on at the time included some collaboration across those systems, as well as some autonomy involved on some of those platforms. In addition to those activities, NASA Johnson Space Center had also had a number of case studies that they were focusing on back then. One in particular depicted here on the left, a human collaborative multi-agent trust assembly test, where you had communications architecture supporting that particular operation. And you see the various types of systems involved, including robots and humans. On the right side, you see a case of robotic tool use involving human-robot interaction, autonomy for assembly operations, as well as provisions for a remote human to teach motion behaviors as an additional agent within the system. And what you see depicted is an architecture for autonomous robots working with adjacent humans. So again, more evidence, if you will, of activity that would apply to things on the lunar surface, but sort of bolsters the suite of algorithms that apply to these types of cases. Here's another one where involving NASA JSC and NASA Ames and some field tests that they were doing in the past. They had a control architecture for human-robot collaboration. And in particular, this system involved a number of different types of AI, from knowledge representation, natural language understanding, learning, planning, inference, search, and vision.
About 1 minute, Eddie.
Okay, thank you. And so this is another example. You see some of the applications there. So the capability of evolution in this regard continues throughout the 2020s. There's a major field test that was done by DLR and others in Europe called the Arches demo. That's one example. Less than a month ago, there was an experiment that DLR and ESA did with NASA astronaut, basically involving the NASA astronaut controlling robots on the Earth surface from the ISS. And then surface robotics, telerobotics from orbits is another area. This one in particular, although it's involved in teleoperation, it's also relevant to collaborative autonomy, since the same systems tend to involve, to some degree, autonomy on the actual platforms themselves. Now, this was mentioned earlier, Cadre. This is a up-to-date flight mission that's supposed to fly at least as early as next year in the Lunar Eclipse program. Motive Space Systems, in fact, is just now finishing up delivering flight hardware to JPL for this mission. So this is a current and prime example of collaborative autonomy about to actually happen on the lunar surface. There's workshops and there's conferences coming up as well. But to the conclusions that I want to point out here, I think that collaborative autonomy proofs of concept abound, including prototype, protoflight, and flight system implementations. But the capability gaps and so forth may be more associated, in my view, with the hardware that can host the autonomy. We need to graduate, if you will, from non-flight systems to real systems that can actually work in the lunar environment and host the autonomy that's on board. In multi-agent collaborative systems area, there's room for improvement in the autonomy advances, but a large body of knowledge is already available in Earth-based collaborative robotics literature, as well as in the open source and open systems community. And finally, robotic intelligence and human interfaces. I think that cognitive intelligence is an area that needs some attention. We need to make robotic systems smarter. We need to leverage and advance the cognitive architectures that are out there. And then on the side of human interfaces, we need to find a way, particularly for astronauts, to interact with our robotic systems in a collaborative way on the surfaces of the moon without having monitors to look at and keyboards to press. So there's a number of different things that we can look at there. Some work has been going on at EPL and in other areas that would apply to this. So I'll stop there. Thank you.
Thanks so much, Eddie. I think next we're moving on to Lynn Regia from Johns Hopkins Applied Physics Lab. So she'll be talking on human-machine teaming challenges for future operations. Are you able to share slides, or would you like us to?
I was talking to Christina in the chat. I think she's going to share slides.
Awesome. Thanks.
I am also more than happy to do it if desired. So yeah, while we're pulling up the slides, I'm Lynn Regia. I am a group supervisor at APL. I actually started here around 15, 16 years ago. I came out of school with a computer science degree and then went back and got my master's in human systems engineering, and it launched me into a career and into my passion, which I get to talk to you guys about today. So thank you so much for having me here. It is human machine teaming is my passion. And today I thought I'd talk a little bit about the challenges for future operations. I think human machine teaming is a real important part of our future. And I'm sure you've heard a lot about that today, but also I think it's sort of a community that needs to come together, like all of us, to really solve these challenges. It's not just going to be solved in one place or by a small group of people. So that's why I thought this would be a great topic. And I'm just honored to be here today. So with that, we could go to the next slide. With a quick history of humans and machines, I like to start with. So some of you might remember back in the old days, I sure do, where, my dad in the basement had a computer with ASCII green, games and things we'd play. And it was called a command line interface, where we were giving very strict instructions to a machine. Don't make a lot of sense to a human, but it's how we communicated with the terminal at that point. Even before then, right, were punch cards, which was a whole nother ballgame. And then we kind of evolved when we saw this graphical user interface come to the forefront. And that's a metaphor to the world around us, right? You have folders on your desktop of your computer in the same way that you have folders on your physical desktop, right? Those manila ones. And it made more sense intuitively. And one of the ways I see the interface evolving over time is we're headed more into what you might call natural user interfaces, where we naturally interact with systems in the same way we naturally interact with the world around us, by saying things, by moving our eyes, by moving our hands, by making facial expressions, right? And so it's a really interesting time in the world of understanding how that future is going to play out. And the future, I think, on the next slide, is is going to be pretty incredible. There's this autonomous system ability, and AI is driving all kinds of new ways we can interact with these systems. And I think unmanned platforms are going to be everywhere. I think they're not going to necessarily be as constrained by size and swap as they are today, thanks to things like advanced materials and all kinds of cool stuff. Every shape and form factor, advancements in power are going to really sort of advance what they can do and for how long. And I think they're going to be able to do things we haven't even realized are possible today, these machines that we're interacting with. But, and the next slide, my further theory is that the future role of humans doesn't go away, right? It's just that we shift. Perhaps the roles of humans changes in relation to those machines that we team with. So moving right along, when I say human machine teaming, what is it that I mean? And I should give a good shout out here while I'm talking through these slides. I see John Gersh is on the line, and he's been a collaborator with me in many of these slides. So John, I'm sure that you are getting some, you're seeing some familiar stuff here. So what is human machine teaming? Honestly, I don't think there is a single agreed upon definition, right? There isn't a sentence that the community of the world at large in this area has really agreed upon. APL, at least our team, took a stab at what that definition could be, as did many others, and ours is kind of represented there at the top left. The study and practice of collaborative bidirectional integration of human, blah, blah, blah. The few key words that I want to kind of hone in on here are integration, dynamic, right? And bidirectional. So bidirectional meaning it's not a one-way street from the human to the machine, it goes both ways. And dynamic meaning sort of some of these adaptive mechanisms. And many of you, if you were in that trust and autonomy session earlier, heard us discussing some of that. And so it's really about this sort of symbiotic kind of relationship. So regardless of how you define specifically HMT, if you look to your right, there's kind of two buckets I like to bin it in. Obviously, it's an oversimplification and you could, there's lots of overlap, but just to kind of frame the conversation, crewed uncrewed teaming is there's some autonomous system out there, right? A robot or a UAV or something that's perceiving, deciding, acting on its own, and perhaps teaming or communicating with a human in some way. The symbiotic side is kind of the closer into the human element, where the system can sense the state of the human and adapt to it in real time, maybe provide information to the human before they even request it, right? Or things of that nature, knows where the human's looking, what they're trying to achieve, and becomes a true teammate. And regardless of what bin or which combination it falls in, I've kind of listed four main pillars there that make this area very hard. And that's what we're kind of talking about today, right? The challenges. Appropriate calibrated trust. We heard a lot about that today. It's too much trust is no good. Too little trust is too good, is no good. You want the right amount of trust at the right time to make this a really productive relationship. Shared context and intent. That's speaking to the complexity of communication between a human and a machine, wherein, so for example, say I say, Danielle, don't let anyone in the door behind you, right? If there is a door behind her, pretend there is. And she might lock the door or put a chair in front of the door or yell at people if they try to come through the door. A machine, if I say, don't let anybody through the door behind you, well, maybe the machine knocks the door down, right? There's no more door. It's broken. It's gone. There isn't a door. No one can go through it. So, and that's just a very simple example. There's a lot of complexity in how we share intent and meaning. Ethics and policy, just because we can doesn't mean we should. And in fact, we as engineers are responsible for what we put into the world. And in this area, we're doing things like handing power over to autonomous systems and hooking systems up to human beings and sensing their information. So at the engineering level, we need to be involved with those ethical and policy discussions. And then finally, sort of the who does what when or how, the optimized teaming elements of workload and decision-making, how do we do those things appropriately with machines and people? So real quick to the challenges, and then I'll get off the stage. If you jump to the next slide. So a few challenges. First, every human is unique and every machine is unique. And those humans and machines evolve over time. New algorithms are being evolved over every day, and machines that are AI based are evolve on the hourly basis based on, you know, what kind of training they get. I, as a human, am a different human being depending on whether I've had my coffee this morning or not, right? I will make different decisions day to day and be more effective day to day, depending on a lot of different elements. The next challenge I want to kind of bring up as to why this is difficult to do on the next slide is that, and it's kind of a myth, we think that more autonomy, more automation, more UAVs is equivalent to reducing human workload and kind of the risk associated or the cost associated with that. But that's not necessarily true. This is actually a very hard thing to do, this optimization. So if you jump to the next slide, we're going to go really quick through these. Imagine we have a mission, we have a planning session, and then we actually go and implement that mission, right? The operations, we execute the mission. And we decide, you can hit forward, that we want to reduce the number of operations, the number of humans involved in the operations level. Click, you can go forward. And then, so automate all the things there. One more forward, please. So then we've done that. We succeed, we insert some machines, the humans are no longer doing that element. Next. And then what we didn't realize though, whoopsie, is that to do that, it's infused an element of planning that requires many, many more humans to be involved up front. And so with the final sort of capture on this slide, the bottom line, if you move forward once more, is that defining who does what when is very difficult, and it depends on what it is you're trying to accomplish, other than just infusing autonomy. That's not always the right answer. And even when we are confined to these small mission sets, thinking broader is often really imperative, and it has unintended consequences when we don't think about it. So next, I think I've got two more slides.
About 2 minutes left.
Perfect. So defining the human machine roles, this slide is speaking to the fact that we often weigh our risks and benefits differently when considering humans and machines. If a autonomous vehicle crashes, right, there's often a lot of news and fallout from that, whereas crashes from humans happen every day. And maybe that's not a perfect example, but the point is that we often think about holding machines responsible very differently than we think about humans. And can you even hold a machine responsible, which is what we're talking about on the right. The thought of accountability when it comes to human-machine teaming is an unsolved and evolving challenge. We really haven't figured out that policy piece yet. So, and then finally, on to the last slide. I just wanted to leave everyone sort of on a more positive note. So I've gone through all these kind of big challenges, each one of which I could talk forever about. But the point is that there's a lot of reasons that we want to improve human-machine teaming, bring more machines into the teaming hemisphere, right? And increase the number of machines that a human can team with. Instead of one-to-one, make it one-to-many. Those reasons could be everything from being in more places at once, doing more things, doing things faster, making better decisions. All of these things are things we want to explore, and hopefully human-machine teaming can help us do. However, there are big challenges with each of those, right? What does a good team even look like? Is a subjective question. So what I'll leave everyone with, and hopefully this just got your brain flowing with thoughts, is that human-machine teaming as a whole is not static, one and done. There isn't some optimal solution there, but as technology and humans evolve, so will our creativity and desire to use it. And so the future is incredible, and I believe it will take all of us to solve these challenges, and I'm just very excited to see where it leads. And I will end there.
Thank you so much, Lynn. That was an amazing presentation. I think it was very inspiring in terms of human-machine teaming. So I guess with that, we'll move on to our last presentation from Dave Handelman. So if we have the slides up, sorry.
Oh, actually, yeah, you can hear me, right?
Yes, we can.
Yes.
So
I'll drop the slides if possible. So
yeah, absolutely.
and I will turn off my video to save bandwidth. So,
Awesome. Thanks, Dave.
all right. All right, so what I'll talk about very briefly is human machine teaming research we're doing. The issue of, we're very interested in biologically inspired robotics so as to have smart machines and adaptive teams. So we're interested in a lot of high level things, such as what Eddie talked about with cognitive intelligence and such, and working from a common playbook. So we have research funded by ARO on that. I actually won't touch on that. What I am going to talk about here is an approach we're taking toward dexterous manipulation by robots, and it's not as much autonomy as control by a human, but dealing with time delay. I mean, one of the points that we want to stress is a belief is that as we make machines more and more autonomous, they're not going to be perfect. The autonomy may have difficulty or break down at points, and having humans contribute to, in this case, manipulation should not be an afterthought. It should be designed in. And so what I'm going to talk about is a way to intuitively naturally control dual arm robots, including with time delay. So I'll try to describe this real briefly. First of all, is the video playing reasonably smoothly?
Yes, it looks great.
Okay, great. So I've been at APL about 7 years. My background's in controls and dynamics. Again, very interested in learning from biology, how to control systems, in this case, limbed machines. This is the modular prosthetic limb we're showing here that at APL we developed with some help of the DARPA Revolutionizing Prosthetics program. So we have a long history in trying to address the issue of very dexterous machines. How do humans control dexterous machines? Ultimately layer in autonomy, but also how do we get it to do what we want? How do we do what we call human capability projection? So this robot here is Robot Sally, 2 modular prosthetic limbs for arms, mobile platform. An operator is wearing sensors. The operator's joint angles are being mapped to the robot, and that's one way to control the robot. You can do very dexterous things, but that's inconvenient. What we want to do is roll in some inverse kinematics and let the operator just say where they want the end effectors to go. So here, there's a leap motion sensor under my hands, and I can control how Robot Sally's arms move in this case. Again, not the most convenient interface, because there's this issue of when do I clutch in? When am I controlling the machine? When am I not? I don't want to be wearing sensors and go to scratch my ear and have the robot do that. There's got to be a way of clutching in and out. So here you see a system where we're using a VR system to control the robots, the manipulators. I'm pressing and holding a button with the Oculus Touch controllers in this case, and I'm flying the grippers. So I'm controlling 7 degrees of freedom in each hand. So position orientation on each gripper plus opening and closing of the gripper. This is a simpler manipulator, Canova Jaco arms. But one of the things we're very interested in is how do you manage the degrees of freedom you want to control? So for example, when you grab a rigid object with 2 arms, it's a closed kinematic chain, and you don't want the operator to have to move very carefully with 2 hands while the robot holds onto something with 2 hands, a rigid object. So in this case, we can press a button and virtually couple the manipulators so that they move in unison. So I can control that coupled set of manipulators with fewer degrees of freedom. I can also control them with 2 hands. If I'm kind of clutched in with both hands, it uses the midpoint between my hands as a control reference. And so we're coming up ways of conveniently controlling a dual arm robot, in this case with an immersive system. Here you see, this is sped up a little, but I'm trying to change a tire with these manipulators. And so tool use and such becomes relatively straightforward with this kind of system. Here, there's stereo imagery coming back from the camera, the robot's head, which is slave to my head in terms of position orientation. Stereo imagery is coming back to the headset, and I have depth perception. So this is a convenient way to control the robot, again, all in real time so far. And this is a demo we did at the DARPA Robotics Challenge Expo, 2 dual arm robots collaborating in casualty evacuation scenarios. So we're always looking for practical applications for this. We've done a lot with explosive ordnance disposal with the Navy and such, for example. So we've developed a method for accommodating time delay, latency. So here is the same VR system. Instead of stereo video being passed back to me, there is a point cloud from a point cloud generating sensor. So there's a 3-second time delay. In this case, there's a barrier between me and the robot. I can't see the robot.
Store and forward. Immediate send.
So in this case, The operator, again, I hold a button to move a model. So this is model mediated control. So what I see is a point cloud coming back from the robot. I'm still intuitively controlling the robot. I'm moving a model of the manipulator, but I can see what the robot's going to do 3 seconds later. When I move the model, it turns red. That means commands are being sent to the robot. And then 3 seconds after that, I see the point cloud move. And so the model in that case goes transparent, so I can see what the actual result of the robot motion is. And so what this allows you to do is, again, use a real-time natural approach for moving the manipulators, but deal with time delay. So the point here is to do a piece of the task and see what happens. And ultimately the robot, as it gets smarter and smarter, I can do more and more of the task. And so what's interesting is that I have a virtual viewpoint, so I can change my point of view from the physical robot, given this 3D point cloud. And I can ultimately perform tasks in an iterative fashion, but again, in a natural real-time way. So here is another mode where instead of
store and forward,
immediately sending
ready to
commands
record,
to the robot,
waiting to start recording,
I control the
recording.
model in real time, but it's not yet sending commands to the robot. It turns
recording
green,
stopped, ready to
which
send,
means I'm
replaying,
basically recording a motion. And if I like it, I can send it to the
ready
robot.
to send, sending,
Here I sent it. Robot moves 3 seconds later.
ready to record,
And then 3 seconds later, I see what happens. But now we speed it up. The point is, I can practice a maneuver. If I don't like it, so how do I want to grab this rock? I came in from above, didn't quite like that approach, so I canceled that practice maneuver, and I approached the rock a different way. And so the point here is, the model mediated approach, I can either directly send commands to the robot, or I can do this store and forward approach where I'm practicing a maneuver. But this is a interesting way to control the robot, and allows you, the time delay can be much greater than 3 seconds uplink and downlink. In this case, it could be much more dramatic. But I do a piece of the task and go get a cup of coffee. I see what happened. And I do another piece of the task. And so this is an approach we're taking to model mediated control, dealing with time delay. And we've looked at doing
immediate send,
real tasks like, digging. And I know time's up. You can manipulate tools as you can in real time. In this case, doing digging. So I'll just kind of speed through this. So here we're digging through a trowel. We also experimented with picking up a spectrometer. It wasn't connected, but to see if physically the robot could ultimately reach out, grab a tool that otherwise a human would pick up, and do a simulated inspection. And so again, I'll speed this up.
About 2 minutes, Dave.
Sure, thanks. So again, we're very excited about this approach because it combines real-time natural motion in terms of what you as an operator are doing, but allows you to deal with time delay using the model mediated approach as an intermediary between you and the robot. And so again, this is intended to be either a primary way of controlling a robot, where we want humans to essentially be performing the task, or we believe it's going to be a method whereby we set up autonomy to do most of the work, but if something breaks down, a human can step in and perform a lot of the task. And so we believe this is, approach to collaboration and human-machine teaming. As I said, we're also working on the Army, looking at higher level types of emulation of human skill. For example, these pictures show we have experiments going on with people wearing HoloLens, teaming with Spot robots, working from a common playbook. And it all fits together in terms of an approach to ultimately delegating more and more authority to machines, but ultimately have a good human-machine teaming interface so that we can interact and collaborate effectively. So I'll end it there and leave a little time for Q&A.
Wonderful. Thank you so much.
My pleasure.
Christine, if you're around to share slides again and throw it on the Q&A. Awesome. So just as a reminder, you're able to go into Slido and ask questions there. And if we don't get to your question, looks like we only have a couple minutes for questions, then we'll happy to gather them up and send them to the presenters afterwards. So it looks like a lot of the questions for the past 3 presentations, and Lynn and Eddie, if you're able to hop back on too, that would be great. A lot of the questions have to do with kind of multiplicity, and for good reason. We're kind of dealing with swarms and machine teaming. But there was a question about using several small robots or rovers in a swarm rather than one large one. And there was also a question about using more than 2 arms in a robot system that such that Dave was looking into. So are there pros and cons to using maybe a lot of small things rather than like one big, well thought out system when it comes to teaming? And that can go to
Yeah,
anyone.
this is Eddie. Yeah, this is Eddie. I can respond. I see things certainly. It depends really on the mission and the task involved. Certainly for situations where a single robot cannot perform a task, such as carrying a large object on its own, whereby help from another robot or even a human might be involved. Those are situations where certainly more than one would apply. But I think there are certain jobs, if you will, for example, surveying of terrain, that a single robot could do, but you get certain level of force multiplication, if you will, if you apply a multi-robot system to actually do that job. So it really kind of depends. There's lots of trades to be involved, and certainly there's the upmass that a particular mission may or may not be able to afford for landing one versus multiple systems at a given location or a given mission. So it really kind of depends, but the answer in short is yes, there are advantages.
Let me just add, I agree with Eddie, it depends. With regard to manipulation, for example, we always have to ask, do you really need human-like manipulators, hands? How many arms do you need? How many degrees of freedom? Because with the degrees of freedom comes complexity and cost and the risk of something breaking down. So, in my opinion, you need to work backwards from what you want it to do to help drive the design, not just of the hardware, but of the software. So those curves have to cross where the complexity is worth it in order to get the job done. And that may be easier said than done, but it's that trade-off, sort of a classic trade-off.
Yeah, I'll just double down on what my colleagues are saying. It totally depends, right? I think that there's lots of reasons, kind of towards my last point about why many things could be useful, right? You have redundancy in functionality. If one thing dies, you have another. You can be in a lot of different places at once. There's all kinds of reasons why you might want a lot of things. In air and missile defense, which is my background primarily, being flexible as far as where physically you are around the world is something that we really, that helps enable. But, and then from a challenges perspective, of course, right? How do you do the C2 challenge, kind of the command and control elements of humans controlling or collaborating with many, many machines versus one, which is kind of more what we have today. That's an open challenge that we're still exploring how to do right. And again, it seems like the answer is it depends.
Yeah, great answers. I agree. And I think a lot of it has to do with kind of, how on an individual human perspective, how are we able to handle, these multiple rovers or spacecraft or robots, and then how do we drive a system that will be able to take in all that data and manipulate them. So great answers. And thank you all for your presentations. In the interest of time, I think we're going to move on to our next quick break. So we have another poll open for you all. These are, so kind of going back to the Lunar Proving Grounds definition workshop and talking about how some of that fills into our autonomy workshop here. If you have a second, please hop on and go ahead and take that poll. Otherwise, we'll see you back at 3:35. Thanks.
Thanks, everybody.
Oh, I guess it would be helpful if I unmuted. Welcome back, everyone. I hope you had some good coffee. So at this point, we'll be moving into our second networking discussion breakouts. So we have human-machine teaming and then machine-machine teaming or swarms. So human-machine teaming will be Zoom rooms 1, 2, and 3. Machine-machine teaming swarms will be 4, 5, and 6. I know last time it was a little bit hectic. So those of you who are hosts and co-hosts, if you could please try to get everyone, the facilitators and the SMEs, to the correct spots, that would be great. If you are in a session and you would like to be in the opposite session, please let any facilitator know, and we'll try to get you into another room. But that being said, let's get to it. So Katina, if we could start the breakouts, we'll jump in. Thanks. We're just gonna oh, no worries. Okay. We didn't get to any content yet, but yeah, Mario,
Can you hear
thank
me
you
all right?
for yes, can hear you all right. We'll
All right,
move
awesome.
to some closing remarks.
Sure. Thanks, Danielle. Hi, everyone. My name is Mario Lento, and I am the Extreme Access Focus Group Facilitator for LSIC over here at Johns Hopkins Applied Physics Laboratory. And it's my pleasure to address you all today as day one of this venture comes to a close here. In my role here at LSIC, I've had the honor of working alongside our Autonomy Workshop Organizing Committee to put together the programming that you've taken part in today and will continue to participate in tomorrow. And before I give you all a summary of today's events, I just wanted to give a special shout out to Danielle, who has worked tirelessly these past few months putting everything together for this workshop. There have been many emails and a lot of meetings to put all this together, and she's done an amazing job behind the scenes, and I'm proud to have worked with her on this. So we entered today's workshop with the goal of gathering you all in the lunar community to exchange ideas on autonomy in support of presence on the moon. And with that in mind, we all saw a very exciting lineup of panelists and presenters tackle the nuance and intricacy of autonomy. In the morning, we began with a welcome and introduction address from Kevin Somerville at NASA, who laid out the context for this workshop and set us up to tackle the rest of the day's agenda. From there, we jumped into that agenda with our first panel discussion of the day, which focused on the challenges and opportunities of developing autonomous systems that are aware of their surroundings and can reason and act accordingly. This discussion was led by our very own Dr. Al-Hassan Yassin, and the panel consisted of Andrew Petruska of the Colorado School of Mines, Emma Holmes of APL, and Rama Shaplapa at Johns Hopkins Whiting School of Engineering. It was in this session we covered topics ranging from general definition of autonomy, misconceptions surrounding autonomy, and how it can be applied to space exploration. One takeaway from the LSIC staff here was that there's a big difference between automation, autonomous systems, and AI. People often confuse them, but they're not the same. Automation is good for repetitive tasks. Autonomy is good for those kind of dangerous or dull tasks. And AI is a tool that can be used to develop and run autonomous systems. After the panel discussion, we jumped into 3 different presentations, the first of which was The Future of Precision Lunar Localization by Alex Pletta and Ben Yunes of Astrobotic. Next, we saw Autonomous Systems, Humans, and Reliability by Jim Bellingham of JHU. And finally, we were joined by NASA's Fernando Figueroa in a discussion on autonomy technologies for systems of a moon base. After pausing for lunch, the group came back and broke out those Miro boards and split up into various networking breakout rooms. The first of the 2 topics that we covered there were situational and self-awareness, which were led by Tom Chang and Al-Hassan Yassin from APL and Terry Fong of NASA. The second topic involved reasoning, acting, and trust in autonomous systems, which was led by John Gersh, Julie Obenauer Motley, and Matt Pfeiffer, all from APL. I can't speak for all of the rooms, but I enjoyed the conversation. I was in breakout room 2 with Al Hassan and Raymond Liu. There was a good conversation surrounding situational awareness, situational and self-awareness. What is it, the methods and processes towards achieving it, and the challenges surrounding it. I am hopeful that we can take all of that input in these breakout rooms and synthesize it in a way to help focus our line of thinking in the LSIC community. In the afternoon session, a panel discussion was held on the challenges and opportunities of developing collaborative systems that involve humans and autonomous machines. And this discussion was led by Sarah Hasnan, who was also a vital member of our organizing committee. She led a group of panelists, Grace Gao of Stanford University, Edward Chow of NASA, Julie Obenauer-Motley of APL. Here, there was a higher level discussion regarding things such as, full autonomy. What does that mean? And is it even achievable? Additionally, there was a healthy discussion regarding lessons learned in designing and integrating systems where humans have to interact with autonomous systems. One of the major takeaways from this discussion is that, autonomous systems will require the development of trust, which can be achieved through, much testing to ensure minimal risk. And humans in the loop play an important role in that trust. Again, special shout out to Sarah. As I mentioned, she was an important part of the planning for this workshop. She also thrives as a facilitator for, these type of important conversations. So I was delighted to see her do a good job today with our panelists. After the panel discussion, we were able to see 3 more great presentations. The first of which was Human Collaborative Robotic Autonomy, Earth-Moon Maturation, by Eddie Tunstall over at Motive Space Systems. Then we saw Human Machine Teaming Challenges for Future Operations by our very own Lynn Regia at APL. And finally, again, our own APL's David Handelman gave a talk on intuitive delay tolerant control of dexterous dual arm robots. And I joined that one. I enjoyed the videos with time delay and human teaming with machines with the robot arms. That was a lot of fun. And finally, we return to our beloved Miro boards yet again to carry out a discussion of 2 important topics. The first being human machine teaming, which was led by John Gersh, Matt Pfeiffer, and Bobby Wilson, and Bobby Wilson of APL. The second conversation surrounded machine teaming and swarms, and this was led by Jean-Pierre Delacroix, Amr Rahmani, and Terry Fong at NASA, and Bam Bamberger at APL. I was in the room focused on the first topic, human machine teaming, and there was a fun conversation in our group regarding APL's own autonomous activities on campus and the potential risks and challenges associated with performing these activities with people all over. Again, I'm hopeful we can take all that input from the Miro boards, from these breakout sessions, and synthesize it for the LSIC community. So in conclusion, I want to thank you all for coming. Thank you for participating in Slido and Miro, in the breakout rooms, through Zoom chat. To all our panelists, presenters, SMEs, and facilitators that contributed to today's conversation, we thank you for your time and efforts. The discussion today was important and exciting, and for all those folks on the agenda tomorrow, we look forward to continuing this conversation then. I can't wait to see you all again in day 2 of this workshop, which starts, as you can see on the slide there, at 10 a.m. Eastern. And with that, I'll turn it back over to Danielle to adjourn for the day. Thank you.
Thank you so much, Mario. I think that was a fantastic summary of day 1. I could not have come anywhere close to doing a better job. Like we said, tomorrow starts at 10. We'll have the same format kind of as we did today, but tomorrow's sessions will be focusing on lunar applications in autonomy and challenges in autonomy. So we'll have a whole new set of panelists, presenters, and wonderful Miro boards for you all to participate in starting tomorrow. So thank you all for your participation today, and we'll adjourn for the day. Thanks.
Thank you, Danielle.